So we've talked about atoms and construction of the atom. We've talked about the wave-like properties, the particle-like properties of light, matter, and electrons. We've talked about the Bohr model. Let's pull it together. So we have this idea of the Heisenberg uncertainty principle. Niels Bohr suggested initially that electrons existed in orbits. Now we know that it describes hydrogen perfectly, but we know that it doesn't describe the other species perfectly because the electrons don't have a fixed path, but rather probability of being able to be found in an area. Quantum mechanics treats electrons differently. Quantum mechanics says the electron has both wave-like and particle-like properties, hence the word wave-particle duality. The Heisenberg uncertainty principle says it's impossible to know both position and momentum of a particle simultaneously. And mathematically can be solved like this. And if you are a chem major, possibly biochem major, you will see this come up later on when you get to PChem, okay? But the consequence of this is that we have no way of measuring an extremely small object's location without disturbing and affecting its velocity. So again, the Heisenberg uncertainty principle tells us that we cannot know both the exact position and the exact momentum, meaning speed and direction, of an electron at the same time. The more precisely we know one of these, the momentum or the position, the less we know about the other. This means that electrons don't orbit the nucleus in neat, predictable paths like planets around the sun. Instead, we can only describe the region where an electron is likely to be found. It helps us explain why the Bohr model is too simple and ultimately incorrect. It supports the idea of orbitals, regions of space where electrons are likely to be found, which is central to understanding the modern atomic theory. But it also shows electrons behave more like fuzzy clouds than little balls on tracks. For an analogy, imagine you're trying to take a picture of a hummingbird in flight. If your camera captures a sharp image of where it is, the wings might be blurry. You've lost detail on its motion. If the wings are crisp, you might not know exactly where the bird was, because it will blur out the background. Electrons are kind of like that. They're too tiny and fast for us to pin down both position and motion perfectly at the same time. So an electron will either act as a wave or a particle, but not both at once. The reason that this statement is made is that the moment we treat the electron like a wave, it behaves like a particle. The moment we treat the electron as a particle, it behaves like a wave. Because it's so small and so fast, we can't have both at the same time. Because of this, we can't assign fixed paths for the electrons. The most we can hope for is knowing the probability of finding an electron in a given region of space. Since the electron has both of these properties, wave-like and particle-like properties, quantum mechanics is also referred to as wave mechanics. QM stands for quantum mechanics. Okay. So again, QM, quantum mechanics, is the mathematical description of an electron. And we from that we get Schrodinger's equation. You are not solving this in this class, it's an upper level class concept, but Schrodinger's equation can be used, solved to describe the electron. Many people have heard the joke about Schrodinger's cat. When Schrodinger first wrote up this idea, he wrote up about a cat. He said basically place the cat in a box with a bottle of poison, and you don't know if the cat's alive or dead until if you open the box, then you break the poison, and then you've affected the life of the cat. But before that, you don't know if the cat is alive or dead inside the box without disturbing it. So Schrodinger's equation, they treat an electron as a wave function. A wave function gives you that orbiting of that electron. Four quantum numbers tell us the most probable location of an electron. Think of it like the address of the electron. Psi squared, your wave function squared, is the probability density. It's a probability of finding an electron at a particular point in space. Schrodinger's equation can only be solved exactly for hydrogen. However, adjustments can be made to the equation for factors such as electron-electron repulsions and other atoms, which can get us an approximate solution. So we can get close, but we can only actually solve this for hydrogen directly. And this is what wave functions look like. So you've got your wave, you got your nodes. Nodes in the function is where there's probability of drops to zero of finding the electrons. So basically what this means is when this is solved, we get probability areas of where the electrons can exist. And then we have nodes where the electrons can absolutely not exist. And this develops into the different orbitals we have. And we know the different orbitals the electrons are in. So your quantum numbers, again, when placed in an equation, these four quantum numbers, give you a plot of points for the region of highest probability of finding an electron. They describe the space the electrons occupy in terms of distance from the nucleus, which is your energy level, the shape of that orbital, which is called your sublevel, the position with respect to the axis, we'll talk about what that means, and the direction of spin. We call this N, we call this L, we call this M sub L, and we call this M sub S. So we have four different types of orbitals that we're going to talk about, specifically S, P, D, and F orbitals. And some of these orbitals have a suborbital for each one. So like S orbitals only have one shape, but a P orbital has three shapes. This describes the shape. This describes the type of orbital, which is the overall shape. This describes the orientation of that shape, of the shape above. And again, I'll show you what I mean by that in just a minute. But basically, these four quantum numbers act like the address of the electron. They tell you your city, state, street, and number, the energy level, the sublevel, the orbital that it's in, and the spin of the electron. Is it spin up or is it spin down? So there are rules that we follow for quantum numbers, and you should understand these rules, okay? The rules are as follows. N is called your principal quantum number, and it's describing the shell of the electron or the energy level you're in. The lower N is closer to the nucleus, and it technically goes up to infinity, and that's furthest from the nucleus. L is called your angular momentum quantum number, but it's describing the shape of the orbital. You need to memorize this. Okay, just flat out memorize it. If L is equal to 0, it's an s orbital. If L is equal to 1, it's a p orbital. If L is equal to 2, it's a d orbital. If L is equal to 3, it's an f orbital. So L equal to 0, s. L equal to 1, p. L equal to 2, d. And L equal to 3, f. Your L values can be anything from 0 up to n minus 1. So technically speaking, they can go up past that. Once we get past F, then we start calling the orbital G, then H, then I, then J, then K, then L. M sub L is your magnetic quantum number, and it describes the orientation in space of the orbital. Again, I'll show you what I mean by that when we start drawing them in a minute. But your M sub L value goes anywhere from L through 0 to positive L. So if your L value is 0, your M sub L value can only be 0. If your L value is 1, your M sub L could be -1, 0, or +1. If M sub L is 2, or sorry, if L is 2, your M sub L can be -2, -1, 0, +1, +2. And if your L value is 3, your M sub L value can be -3, -2, -1, 0, +1, +2, and +3. And then M sub S is the spin of the electron, +1/2 for spin up, -1/2 for spin down. So the orbitals themselves, what is the physical meaning of psi? If I do psi squared, if I quanti, quantifying this, that is called your probability density. It's representing the probability of finding an electron in a given volume of space. So when Schrodinger's equation is solved for the lowest energy electron in hydrogen, you get a 1s orbital. When I plug in the values for the lowest energy electron in hydrogen, which has an n value of 1, an L value of 0, an M sub L value of 0, and an M sub S value of +1, 1/2, I get an s orbital. And the s orbital is just a sphere. The If I have a 2s orbital, it's further from the nucleus. It's a second energy level. 3s orbital, even bigger. And we're going to draw these out in just a minute. So you guys are not responsible for them yet, but like 2s, 3s, okay? And you can see here, the picture here, the electron probability versus distance from the nucleus. We see our 1s, our 2s, and our 3s. We have our nodes in between. So there's a node here for the 3s where the electrons can't reside. There's a node in your 2s where the electrons can't reside. Electrons can, that's the space in between. What an 1s orbital actually looks like when solved is this kind of fuzzy area. And basically it means that the electron, this is the probability of finding an electron in this area. The thicker the dots in the center, more likely to find that electron. The further out I get, the less likely to find the electron. So it has an area it's allowed to be in. Probability density, how likely am I to find that electron? Now we are going to watch this video really quick. I want to give high credit to Minute Physics for this video. It's a great video. It describes these very, very well. And so it's going to describe what this means by the quantum numbers and what these orbitals are.
Thanks to Google for sponsoring a portion of this video, for supporting small businesses, and for helping people find jobs. More about all that at the end. Atomic orbitals have long been a source of frustration for me. On the one hand, you have simple cartoon diagrams that make them feel friendly, but which are so varied and vague they don't really convey much beyond the basic idea that atoms have a nucleus and some electrons. Some people try to take the cartoony diagrams and make them feel more random or quantum, which is an improvement, but they're still very much just cartoon stand-ins for the vague idea of atom. On the other hand, you have atomic orbitals depicted as fuzzy clouds or balloons or rainbow donuts, which are definitely more technically accurate or technically inspired, but none of which feel like they give me a sense of what's actually going on. Like, what does this blobby thing have to do with orbiting electrons? Is the electron inside it, or on the surface? Why do some of them have blobs and others donuts? And why are some of the donuts rainbow colored? I want to know what an atom looks like, and I want that picture to actually have something to do with the nitty-gritty reality of atoms, since they are indeed real things. You know, like how a diagram of the solar system is both a totally not-to-scale caricature, and yet also represents the very real idea that the planets all orbit the sun in roughly the same plane, and that some are farther out and some are closer in, and if it's animated, we get to see that the closer planets complete their orbits more often. It's a nice picture, and that's what I want for atoms. A good picture. There are a few things I'd like that picture to get across, some of them because they're important for the physics of atoms, and some of them because they're questions my brain wants answers to. Like, where is the electron? How fast is it going? How much energy does it have? How big is this picture relative to other pictures? Of course, the wave-particle nature of quantum mechanics means some of these ideas, like the electron's position, don't translate exactly from our everyday intuition to the atomic scale. But there is a way of thinking about wave-particle duality where you picture the wave function as a bunch of water, and the particle as a speck of dust in that water. The particle is mostly guided by where the water goes, and the water is guided by the equations that determine how water behaves depending on its circumstances. And if you apply the mathematics of that idea to atomic orbitals, and then render it in 3 dimensions, here's what you get. Isn't it beautiful? Here's another. And another. And another. In fact, I made a bunch of these, and they're all mesmerizing and beautiful, and isn't the ground state of the hydrogen atom just so cute? And aren't the excited states so majestic? There's so much structure and detail in them, I just love it. You can see patterns in the orbitals, and you can get a sense that they actually are orbitals. I mean, something is orbiting. Okay, so I do have to be clear. The dots don't each represent a separate electron. The whole collection represents the wave function of a single electron, and the individual dots represent all the places that electron could be. A higher density of dots means a higher probability of the electron being there. The bigger orbitals are the ones with higher energies, because electrons with more energy are more likely to be far away from the nucleus. The motion of the dots is showing the flow of the wave function, and does correspond to an extent with its actual angular momentum, though they're not electron trajectories. Unless you think Bohmian trajectories are real, in which case they really are electron trajectories. I'll let the philosophers of physics fight that one out. But the point is, these visuals are created by representing actual electron wave functions in a visual language that our brains can understand, that of objects and light and shadows and motion in 3D space. There's actually stuff orbiting, and they're pretty. I hope you like them as much as I do. Oh, one final thing. I 100% get that these are not easy to draw. So if you want a cartoon representation of an atom that's simple but more closely based in atomic physics, here's my proposal. It's based on the orbitals from the p block of the periodic table. One of them has the electron orbiting one way, one in the opposite way, and in the third one the electron is orbiting the same amount, but around some perpendicular direction, and we can't know which is why the dots aren't moving in the middle orbital, and why I've drawn a dotted line and question mark for the sideways circle. And if you want, you can add an electron to each orbital, or 2 electrons, one oriented spin up and one spin down. This is a Minute Physics approved cartoon representation of an atom. but really, the beautiful 3D ones are where my heart is. Thanks to Google for sponsoring this portion of the video. When Google reached out to sponsor Minute Physics, I immediately said yes, because I use Google search literally every day for everything from 3D software tutorials to physics questions, the weather, recipes, and of course, coronavirus vaccine information. And Google has been focusing a lot on supporting individuals and small businesses over the last year. Google
So hopefully that video helped and can make a little more sense of trying to explain this idea of probability of where the electron resides better than I can. We do have these allowable energy levels. So we have to understand the different orbitals. You guys are responsible for drawing S, P, and D orbitals. You are not going to be drawing the Fs, okay? So S orbitals are just a sphere. You've got the 1s, the 2s, the 3s. You can see they get bigger in size as they go. 3s is just further from the nucleus, and that's why we see it's bigger. Okay, further from the nucleus than the 1s. And then in here you see your nodes. So the 1s, the very center here is your the center here where the white is where your nucleus is. So you've got your nucleus here, and then you've got your node in the species as well. You can see the nodes here. The node is the white area in here, and the node is the separation between the 1s and 2s orbitals, or in the case here, the separation between 2s and 3s. And that's where electrons can jump between, but they can't reside in between. That's the idea of quantized energy levels. Like we talked about the stairs when we talked about quantized, we talked about the stairs. It's kind of the same thing. Your nodes are that area in between where the electron can't stop. It has to be in one of the positions, in one of the energy levels, probability of that space of an energy level. And same thing you see here, the more fuzzy pictures, no more solid pictures with the nodes in between. S orbitals, just a sphere, pretty straightforward to draw. The orbitals look like a dumbbell shape or a figure eight, bow tie, whatever you want to call it, but they are specifically oriented with respect to the axis. So if you're going to draw the s orbitals, if I gave you the coordinates, let's match these. So they've got x, z, and y here. This, to draw it, you would just draw a circle. And that's it. You can shade it in if you want, it doesn't matter, but just a circle. Now your p orbitals, a little bit different. You can see them here, but to draw them yourself, you need to be able to draw these. So if you've got your x-axis here, your z-axis here, your y here. The x means that it's centered on that x-axis. And they are in different phases. So you can either shade one side in and leave the other side blank, or I'll show you if you got py, it's centered on the y-axis, which this is going behind you. This is coming out at you on the board. And so you could you can either shade one in or you can write plus minus in them, whichever you prefer. And then PZ is centered on that z-axis. Again, shading in one half of it because they are in different phases. The node in between is where the electrons are not allowed to reside. So the node is where the electrons can jump through, but they can't stay in there. But each shape holds 2 electrons. So overall, the s electrons in total, and like a 1s electron can hold, a 1s electron can hold 2 electrons. P's don't start until the second energy level. We will talk about that. But your 2p's, you have 2px, 2py, and 2pz, and each one holds 2 electrons. So one set of p orbitals holds 6 electrons overall. You are also responsible for drawing the D's, and the D's are a little bit harder to draw. Okay, so you have 5 different shapes for the d orbitals. The other way to remember this too is let me back up to quantum numbers here. If you remember for s, my L tells me L equals 0 tells me it's an s orbital. My m sub L equals 0, which is only one number, which means one shape. My p's, L equals 1 for p, which means m sub L equals -1, 0, and +1. So what that means is that there is 3 shapes. My d Okay, looking at our d orbitals. Remember for d, L is equal to 2, which means my m sub L values, -2, -1, 0, +1, and +2. Each one of these can hold 2 electrons, m sub s equal to +1/2 or -1/2. But that means overall there's 5 shapes. Each one holds 2 electrons, so 10 electrons total. And again, these shapes that we're drawing are the mathematical solving of the orbital. So if I plug these quantum numbers in and solve the math behind it, they actually give me these shapes. These shapes are where the electrons are allowed to be, but that's where the shapes of the orbitals come about, is from the solving of the math behind those quantum numbers. You do have to be able to draw these, though, for the d orbitals. So just like the p's, let's go ahead and draw out. We're going to put our x-axis here, our z-axis here, and our y-axis here. The difference between P and D. On P's, when it tells you the letter, like PX, PY, PZ, it means it's centered onto that letter specifically. On D's, when it says DYZ, DXY, and DXZ, it means it's between those two orbitals. It's on the orbitals when we see x squared, y squared, or z squared. That's when it's actually on them, okay? So first up, let's do DYZ. It's hard to visualize these, but you need to do your best. You got your z-axis here, going up and down on the plane of the board, and your y-axis, I'm drawing it differently than the picture shown. This is what we're going to draw it in class, though. Your y-axis is coming out of the board at you and going behind the board, okay? So you need to visualize that orbitals that are between the plane here. And so if you need to come see me in person off-star so we can explain it and go through it, that's perfectly fine. But you're going to have an orbital here, and an orbital here, an orbital here, and an orbital here. Now, opposite phase, we do shade them in. But, and this is hard to see, and I know it's hard to see, but this orbital here and this orbital here, these are behind the plane of the board, and they're going away from you. This orbital here and this orbital here are in front of the board, and they're coming out of the board at you. Looking at the DXY. Again, we've got your X here, Z here, and Y here. So your DXY, that means that we're centered on the x-axis and the y-axis here. So it's your x-axis is in the plane of the board, but your y is still coming out and going away. We need to find the one that best describes that. So we've got orbitals between there. We've got an orbital here and its counterpart here, an orbital here and its counterpart here. We shade in the opposite phases. But again, just try to visualize it. These two orbitals are coming out of board at you. These two orbitals back here are going behind the board. We then have the DXZ, which is a little bit easier to draw, truthfully. Those two are probably the hardest two to draw. In my opinion, at least, they're the hardest two to draw with our axes, well, the way we have our axes defined. If we define it another way, there'd be a different set that are difficult to draw. So we're just going to define them this way, and this way you'll see them in class. But X, Y, and Z here. So my DXZ means that is between the X and Z axes. My Z axis is here. My x-axis is here, so it's going to be the orbitals in the plane of the board between x and z. I shade in the opposite phases, so again, this is in plane of board. my dx squared y squared, when you have the squared there, that means it's on the x and y axes. So I have a set of lobes on my x-axis, and I have a set of lobes on my y-axis, or axes. So the y-axis has a set on it, the x-axis has the second set on it, and I shade on the opposite side here. And then my dz squared means it is centered on the z-axis. So I put one normal shape here. Now the second one has to be centered on that z-axis as well. Again, this is x, z, y here. So what we do is we form this donut shape to emphasize the second orbital that is also on that z-axis. But there's a node in the middle, so it's hard to see it, but there's a node right here in the middle where no electron density can exist. Electrons can pass through there, but they can't hang out there. And lastly, we have your f orbitals. You're not responsible for drawing the f orbitals. I cannot draw the f orbitals. You're not responsible for naming the f orbitals. I don't know the names of the f orbitals, okay? You are responsible for remembering that an L value of 3 means an f orbital. That means that the m sub L values here are -3, -2, -1, 0, +1, +2, and +3. So again, when someone plugs in the n, the L, the m sub L, and the m sub S, and it happens to be for an f orbital, so like if I have like n equals 4, L equals 3, m sub L equals 1, m sub S equals +1/2, when they plug this into the equation and solve for it, it will give you one of these shapes. Each one of these holds 2 electrons. They're all degenerate or equal in energy electrons, or electron orbitals. They're all completely equivalent. So f orbitals have 7 degenerate orbitals under each energy level. That means in total, 14 electrons can go to your f. As a reminder for the d's, because there are 5 shapes, that means I have 5 degenerate d orbitals under 1 energy level. For my p's, I have 3 degenerate. Per energy level. And for s's, it only has 1 orbital, so they're not degenerate because there's just 1 orbital to begin with.